Welcome to the class Advanced Calculus and Complex Analysis. Today we are going to learn one of the most important formula, Cauchy's integral formula to evaluate the complex integration. So before going to learn about the Cauchy's integral formula, let us go through the Cauchy's integral theorem with the statement where fz is analytic in a simply connected domain D, and then for every closed contour C in D, we will get this integration value is equal to 0. Fz dz will be equal to 0. What is this statement basically is saying? So Fz is analytic in a simply connected domain D. So this is a connected domain, simple connected domain D. Okay, and where CBA closed contour lies inside D. Okay, so what is fz? So here fz, this fz basically this is analytic in D, and what is c is lies inside D. So not only for this c, for any types of simply closed contour C in D, if you want to do the integrations over C, that integration value will be equal to 0. So that means there is no point in D will create problem here. Basically that fz is analytic everywhere. It is every z. So that means, so this integration value we no need to evaluate. It is automatically will be equal to 0. Just okay. So let us solve this problem by using Cauchy's integral theorem. So here evaluate this integration over C. What is that C? C is the circle center at 2. C is the circle center at 2, okay, and radius 4. Fine. So let us draw the graph. I want to see where is that circle. Fine. So suppose this is radius 2 is 2 and it is up to 4. Fine. So that means up to here you will draw a circle. So circle center at 2 and radius 4. Fine. So it is actually 4 point. So now look at that integration. Integration is given. Here I am writing integration is given like this. So it is C fz, okay, fz dz. Fine. So then what is fz? So your fz is basically is equal to z minus 2 that square. So now you see. So what about fz? Is that fz is analytic on or inside C or not? That one you have to actually check. So this fz actually it is the polynomial. Okay, this is the polynomial of second degree. It is z square minus 4z plus 4. Basically it is the polynomial. We know polynomial equations are everywhere differentiable. So that means it is the differentiable not on, so in the neighborhood, and it is also everywhere. So that means this fz, there is no problem for fz for the analyticity. That means fz is analytic on or inside C. So that's why by the Cauchy's integral theorem I can write that integration value will be equal to 0. Yeah. So basically why integration value is equal to 0? Because this fz is the polynomial of second degree. So as it is the polynomial, so that means it is everywhere differentiable. So that means for this C on and inside C it is differentiable, and that means it is actually analytic. So that's why this integration is equal to 0 by using the Cauchy's integral theorem. So now we have learned the Cauchy's integral theorem and one application we have seen. So now we are going to learn the Cauchy's integral formula. So the type is this is basically the Cauchy's integral formula. What is the statement? Where fz is analytic in a simple connected domain D and C is any positive oriented simple closed contour which is lies entirely within D. Then for any point z0 within C, this integration value will be equal to 2 pi I into f of z0. This is very interesting integration and very important one. So let us try to understand what it is saying. Suppose D, this is a simple connected domain Okay. So what about C? So this is, so suppose D is the simple connected domain. D be any simple connected domain. So what about C? C actually lies entirely in T. Okay. What about FZ? FZ is analytic on or inside C. Fine. So now, so not only that one, but so this is also FZ also, it is analytic in the connected domain D, and C is lies in C. So for FZ there is no problem, but I am considering one point Z naught inside C. Fine. So then what about this integrand? Now this integrand actually have the singularity at Z is equal to Z naught. But for Fz it is, there is no problem. Fz is analytic, so it is in T. So but for that Z naught, what about this integrand? So this integrand actually coming the singularity at Z is equal to Z naught. But we can find out the integration value over C, that is actually 2 pi I f of Z. Fine. So Z naught actually lies in C or on C. So for the application of that Cauchy's integral formula, let us evaluate this problem. So where, what is the statement? Statement of the question is evaluate this integration over C, where C is the circle. It is given mod Z is equal to 2. What about mod Z is equal to 2? Mod Z is equal to 2 means radius. About what about the radius? Radius actually 2 and center at 0. Okay, you can draw it. To evaluate this type of problems, you have to draw the graph. Okay, suppose this is the origin, and it is what it's saying. C is the circle, center at 0. What about radius? Radius is 2. Suppose this is 2, and for this radius 2 at center at 0, I am going to draw the circle. Okay, and what about this boundary? Boundary is the positive oriented curve C. So now, so what about that integration? It is given C Z e power Z Z minus 1 dz. Okay, Z minus 1 dz. So now I can write it this form. So C f of Z, okay, f of Z and Z minus of Z naught, because I want to visualize this one as it is the same form of Cauchy's integral formula. So what about Z naught and Fz? So here Z naught is equal to 1, and what about Fz? Fz is equal to Z into power Z. Okay. So now look at here. So what about Z naught? Z naught actually you have to identify, that is 1 where it is, because it is radius is 2. Radius 2, center at origin. So what will be 1? 1 is in between here. Okay. So that means that one point, that Z naught point, so lying inside C. So because as per the statement it is saying Z naught should be on or within C. So here actually we have seen, so Z naught actually in C. So that means we can apply the Cauchy's integral formula. Fine. So here you can write here where, so Z naught is equal to 1. Okay, Z naught is equal to 1, and it is lying, it is lying in C, in C. Okay, and also Fz, what is my Fz? I have considered now Z e power Z. So this is analytic on or inside C. Okay, you can say on C. Fine. So fz is analytic and z naught we have identified actually it is lying in C. That means easily I can use the Cauchy's integral formula. So by the Cauchy's integral formula, by the Cauchy's integral formula, what we are getting? So that is actually basically is equal to 2 pi I 2 pi I f of z naught. Okay. So what is f of z naught? So that means 2 pi I f of 1. Is it clear? So that means 2 pi I f of 1. So what is fz? Fz already you have. So that means it is 2 pi I e. Okay, is it clear? So that means by using Cauchy's integral formula, we have evaluated that contour integrations, but we have not used the our whatever our known concepts from real integration. No need to do that in that form or no need to use any formula, but by using the Cauchy's integral formula, you can find out. But condition is that you have to identify that points where it is lying. Clear? So that point should be actually on or inside C and fz should be analytic and accordingly you have to choose that one. Yeah. Okay. Okay. Now very interestingly look at this problem that C is same and little bit I have changed. So that's why that questions actually now in the very interesting form. This is the integrations. Another factor I have added in the denominator. Okay, what about that C? C in the same form. It is center at 0, radius 2. Okay, so that means you can draw it. Suppose it is 1 and it is 2. It is 2. So accordingly you draw the circle center at 0. Fine. So now it is 1 and what about this is 2. So what about here? It is outside, it is 3. Fine. And center at origin. This is the circle and it is positive oriented. By default we will consider it is positive oriented or anti-clockwise. So now what is your aim? So what is the given question? You write it down. So what is fz? C z e to the power z, it is z minus 1 and z minus 3. Fine. So dz. This is the question. We are going to evaluate it. Fine. So what is your aim? First you consider or set the denominator part is equal to 0. Denominator part, that is z minus 1 into z minus 3 is equal to 0. So then how many roots you are getting? One, z is equal to 1 and z is 3. Okay. So now you identify which point lies actually inside C or which is outside C, or maybe you may get the 2 points also lies inside C. In that case you have to do the partial fractions, you have to separate the factor. So anyhow here let us check here 1 and 3. Where is 1? 1 actually lies inside C. What about 3? 3 lies outside C. So which point is lying outside C? So that one, for that one you have to, that factor you have to consider in the numerator. Okay. So what you are getting from here? So here, so here 1 is lying, 1 is lying inside C, but 3 is lying outside C. Okay. It is outside C. As it is outside C, we will not bother about this point 3. So then what we will do? So that integration, for that integration you have to do some special treatment. How? It is in this form. You see what I am doing. So it is the integration C f of z written like this, and in the numerator it is, in the denominator it is z minus 1 dz. Then what is fz here? Where fz is equal to f z is equal to z e power z, and that name denominator part, that z minus 3, that factor also you include fz, because now this fz is analytic, where fz, this is analytic, this is analytic on C. There is no problem, because these 3 points actually out is lying outside the circle C. Okay, so then by using the Cauchy's integral formula, what we will get? So it is 2 pi I f of z naught. Z naught is 1. Okay, so that means what is 2 pi I? We will get, it is 2 pi I. What is f of 1? Fz is equal to this one. So what is f of 1? So f of 1 will be equal to, it is e power 1 and 1 minus 3. What you are getting? So it is minus 1 by 2 e. Okay, so now this point you substitute it here. So it is minus half of e. So then you calculate it, you are getting minus, and it is pi I, pi I e. Yeah. So you see, just one factor I have added. So that's why some special things you are doing. Okay, as that's these 3 points lying outside C. So that's why this factor you have to consider within the numerator. So that's why this whole term now it is your fz. Because now this, what is fz? Basically in the statement it is saying fz should be analytic everywhere. Okay, so that's why these 3 points not creating problem for C. So that's why I have actually included this one z minus 3 factor here. So what is the remaining one? So that is z minus 1. For that z minus 1, actually 1 lying is in C. So that's why I kept this factor in the denominator. Is it okay? So then we can compare this formula and this form with the Cauchy's integral formula. And by applying that one, we are getting the value minus pi I e. Okay, thank you so much.